Let's move to the last speaker of the first session, Fernanda Roman de Oliveira, a PhD student of Captain Astronomical Institute of University of Groningen. She will talk about a 3D kinematics view of these galaxies at redshift 4.5 with ALMA.
Thank you. Can you see the screen?
Not very well.
No? What's the problem?
No, with the sound.
Hi.
I don't know if maybe it's only my problem, but it's not so clear.
Does it work now?
There is some kind of echo or interference.
Yes.
Well, sorry.
Can you just check if you have the right microphone in your Zoom setting?
Yes. Is it better now?
No.
No? I apologize, but I don't think we can change now.
I think it's understandable, right? So I
Yes,
think,
yes.
yeah, we can go ahead.
Okay. So my name is Fernanda. I am a PhD student at the Captain Astronomical Institute in the Netherlands. I work with Filippo Fraternali, and I'm very happy to talk to you today about my work on kinematics of galaxies at redshift 4.5 with ALMA data. So before anything, I would like to tell you a bit of what kind of information we can get from kinematics and what it can tell us about the galaxy and the formation and evolution of galaxies. So, for example, this galaxy you see here, it's a nearby galaxy at very high resolution, very high signature noise data, and if we take the rotation at every ring, the radius and the dispersion, we can make this rotation curve and the dispersion profile. And we can attach some physical meaning to these values. For example, the dispersion can tell us about the turbulence in the disk. And turbulence can be many things, but most specifically for galaxies, stellar feedback is a big one, where it can also tell us about outflows, inflows of gas, and also disk instabilities, rotational stabilities in the disk. And another important thing that we can do with this is the ratio of the rotation, so V, and the dispersion, sigma. This can tell us how stable it is case. So if we have a rotation that's much higher than the dispersion, it's a rotation supports disk. And if the dispersion is similar to or higher than the rotation, then we have a pressure supported system. So it's not a rotating disk anymore. And especially with the rotation curve, this is very useful because it can tell us about the dynamics of the system. So this rotation curve is the rotation at every point in the galaxy, but it can be due to many things. For example, the mass in the gas and the mass in the dark matter component, and also the stellar mass. So we can actually decompose this curve into all these different components of the galaxy. And we're also going at high redshift. So what exactly do we expect of galaxies at high redshift? Most specifically about their kinematic properties. And within the framework of galaxy formation and evolution that we have right now, we know a few things about these galaxies. One is that they have very high star formation rates, about 1,000 solar masses per year. This is measured. We see this in many galaxies at high redshift, but we expect that this high star formation rate also has a very efficient stellar feedback. This is because these galaxies are still not very massive. The gravitational well that they have is not that deep that it can hold the gas mass, because these galaxies grow through hierarchical growth. So you have many supernovae expelling a lot of gas of these galaxies. And we also expect that they go through frequent mergers at this stage of the universe and with very high accretion of gas from the environment. So with all of these, we expect that these galaxies have very turbulent disks, if they have disks at all. And we can see this in simulations. I bring here the TNG50, so a very recent one. So our theory, as we go to the local universe, we see that the dispersion is very low in the galaxies, but as we go higher in redshift, the dispersion goes much higher as well. So we expect that this redshift of 4 to 5, depends on the mass, of course, but we're expecting to see dispersions of 90, 100 kilometers per second, and with a general V over sigma, so that ratio of rotation to dispersion of 3 or less. And this is actually supported by data up to some extent. If we have plenty of these measurements for lower redshift galaxies, specifically up to redshift 2. And we have this for ionized gas, which tends to be higher, to have higher dispersion, but also for atomic and molecular gas. And if we extrapolate these values to higher redshift, so again, above 4, we also expect the dispersion goes to 90, 100 kilometers per second. And the general V over sigma is also 3 or lower. So with all this in mind, it was actually a surprise that when because this was before ALMA, when we didn't have much detail on the observations. And now with ALMA, we can see many galaxies are actually 4, 5, and even 6 or higher that have features of rotating disks. And some of them have V over sigma up to 15, which is equivalent to galaxies in the local universe. So the main idea of my project is exactly trying to figure out how common this is, and if we have to rethink our framework of galaxy formation, specifically the disk formation. At which point does the disk form in cosmic time? And how turbulent are these disks that we observe at high redshift? And if it's all galaxies have disks that rotate as fast as this, or other galaxies may be more turbulent or don't have disks at all. And for this, we need a large sample. For redshift 4, it's 4 galaxies. We have 4 galaxies at the moment. We're looking at redshift 4.5, and we're looking at C+. C+ is very important. You can see the emission here. It's on the dust continuum, close to the dust continuum. And this is a very good line because it's the brightest line at this redshift. And it's also very extended. It's much more extended than the CO, the traces molecular gas. And we need it to be extended because we want to probe as large as we can in the rotation curve, so we have more information, and we can also tell which point, how much dark matter we have within a certain radius, right? And this is also a good line because it traces the cold gas, not just molecular gas and atomic gas mainly. And we went for the highest resolution possible of about 0.1 to 0.2 arcseconds. At this redshift, it's about 1 kiloparsec, so 0.7 to 1.3 kiloparsec, more or less. And this is very high, but these galaxies are very small. Most of them have a radius of 3 kiloparsecs. So we really need to push for high resolution if we want to have many data points in the rotation curve. And the other thing is how we analyze this data. So we want to measure the kinematics, and we ideally want to do this with the whole information that we have. So we use 3D Barolo because it's a three-dimensional kinematic tool that measures the rotation and the dispersion over the whole data cube of all channel maps, not only on the velocity field. This is important because you get more accurate information, but also because it's very good to overcome the beam smearing effect. And for example, here is the same galaxy that we looked before. In this data with this beam that's just a tiny point, we have a rotation curve with these gray points, very detailed. But if we wanted to observe the same galaxy with a lower angular resolution with this beam that's comparable to the size of the galaxy, we can only have 3 independent resolution elements. And if we do this on the velocity field, we actually get these blue points. This is the 2D measurements. And in this case, we overestimating the dispersion and we underestimating the rotation, which we don't want to do because we want a very accurate idea of how the turbulence is in these disks. And if you use a 3D tool, in this case, Barolo, we can actually measure these red points that fall exactly on the rotation curve and the dispersion profile. And here you can see how the model overlaps the data over every channel map. And finally here are the galaxies that we have. They are very interesting in the sense that you see that we have a very high angular resolution. We have many independent resolution elements over the major axis of these galaxies. And all of them show a very clear feature of rotating disks. Velocities for this one is about 400, and dispersions I'll show you later. But another interesting thing is that although they have very clear rotating disks, some of them still have very interesting features that could be minor mergers or outflows and inflows. You can see this better in the position velocity plot. So on the y-axis, we have the velocity, and the x-axis is the radius on the major axis. In red, we have the Barrow model on top of our data E. And as I said before, for example, this galaxy here, you have a feature that's not reproduced by the model in one of the sides. This could be an outflow. That could be stellar feedback, for example, since it's not in the center of the galaxy. And you also have, for example, this other galaxy with a very big feature here that could be outflow. It's close to the center of the galaxy. The model does not do a good job at reproducing that, most likely because it's a small part of the rotating disk. And what we get from these galaxies is this rotation curves. These rotation curves and these dispersion profiles, just like we got from the first galaxy that I showed before. And we see that we span a different range of rotations. We have one galaxy that's very fast rotating. We have the other galaxies that are less rotating more slowly. And we have dispersions that vary a lot across radius, but they are still quite similar among each other. So one interesting thing is about this dispersion. All of these galaxies have an average across the disk, across all the galaxies, of 70 to 85%. So this is lower than our expectations from the simulations, the theory, and other extrapolation of the data that we had at low redshift. But it's still consistent with the stellar feedback from the star formation rates alone. So we don't need to consider or employ gravitational stabilities to explain this kind of dispersion in these galaxies. And the rotation over sigma, the V over sigma ratio of these galaxies varies a lot. So we have a galaxy with a V over sigma 2 and a V over sigma of 8. So we're seeing a kinematic diversity here. We're getting closer to what we expect from the models in a sense. And in the future, we also want to decompose, we're doing this right now, we're decomposing these rotation curves, which can tell us what's the dark matter content of these galaxies. And very interestingly, we can tell the stellar matter component before we have James Webb, because right now we don't have any information of the stars of these galaxies. And I leave here my conclusions. So the main point is that we do see galaxies with regularly rotating disks at high redshift, and they have turbulences. So the sigma is still a bit lower than our predictions. But the dispersion is consistent with the star formation rates alone that we have measured for these galaxies. And the V over sigma, they are lower than the previous observations, the stunning, very fast rotating galaxies that we have. So maybe we are seeing a kinematic diversity. Not all galaxies at this redshift may have very regularly rotating disks. And we're trying to understand why. Maybe it's those galaxies that have very regularly rotating disks are more massive, and maybe this helps building this disk, this rotation faster. But the main point is that we see, in spite of all the high star formation rates and these features of mergers, outflows, they still have very regularly rotating disks. Thank you.
Thank you, Fernanda. Very clear talk. I see some questions. I'll read in the chat.
So I can read the questions. First one. So thank you very much. Nice talk. How critical for the modeling is the inclination angle of the galaxy, and how well constrained it is? And similarly, do you need to have a good a priori knowledge of the mass of the galaxy in order to set up the 3D rotating disk model? So what about the inclination and the mass of the galaxy in the model?
The inclination is vital. It is actually something that we've been debating for a while for these galaxies. Because there is no other clear way of how we should derive the disk geometry, so the inclination, and also we're seeing that the thickness is quite important as well. We were using we're getting the total map of the galaxy and fitting many different ellipses to figure out the inclination. That's how we find an inclination. It's not by eye. But the problem that we see is if we ignore the thickness, the inclinations that we get are very low. For all the galaxies, around 40. So we're thinking that the thickness cannot be ignored. And we're finding thickness about 1 kiloparsec. So 1 kiloparsec thickness, and then we have inclinations that are around 60, which is kind of what we expect. So the inclination is a very big factor for the uncertainty we have in the models, and we're looking into that right now. The mass, however, not really. The mass does matter when we look into the origin of the turbulence, especially if we want to figure out the disk thickness. If we employ some hydrostatic equilibrium, we're using some measurements of the mass to figure out if this thickness that we measure is consistent, if it makes sense, and this matters a lot, the gas mass that we have measured before. But still, it's within large uncertainties because this data is still low signal to noise. We don't know much. Hope it answered.
I have two questions, and I will merge this question because the question is about mergers.
Yes.
So actually, I also have some kind of similar question: is how can you really distinguish between mergers activities, rotation, and turbulence in these distant galaxies?
Yes. So if we see here, mergers and the rotating disk is somewhat easy because if it's rotation, we would expect that you have a disk with a very clear minor axis, very straight. And for example, this other galaxy doesn't have, it's more like a C. So this whole region does not fit the model of a rotating disk, right? But we still see this pattern of feature, the rotation, and it's most likely a rotating disk with this minor merger, but we cannot really distinguish what's a minor merger from an outflow and inflow of gas. It's still a bit hazy. And we are at a resolution, for example, especially for this first galaxy, we have five to six independent resolution elements. It's very unlikely that this could be two features merging, two smaller galaxies merging, because then you wouldn't see an accumulation of emission that's flat on both sides. You would see more like two blobs. It's a bit different, especially at this resolution. We would expect to see it.
So
maybe
I missed a question.
No, just a comment that maybe the kinematic is dominated by the rotation in these cases, right? Yes.
But of course, you still have these features of possibly outflows or minor mergers, inflows. That's hard to disentangle.
So this is actually kind of a surprise, right? That you see already so well organized the disk rotating and in the far universe, right?
Over different masses, over different star formation rates. Yes.
And Fernanda, sorry, maybe I miss. How do you select your targets?
So we selected, these are all.
And why the redshift 4.5 and not other high redshift?
Yeah, so we're interested in redshift 4 to 6, 4 to 5, because this is where we get the C+ line, very bright, very extended. A redshift 6 and above, it's more O3, and that's ionized gas, which again, I said the dispersion is a bit higher. It doesn't really probe the cold disk that we want to see. So this is why the redshift. And the selection was, this is all public data in the ALMA archive. We went for the highest sensitivity and highest resolution that we could possibly get. And then we found these 4 galaxies.
And are you planning to enlarge the sample?
Yes, I did put a proposal for ALMA. It didn't go through last year. We'll try again. But there is also other proposals that try doing the same. There's triceps right now. The data is not public yet. There is also the large samples with Alpine and also Rebels, but those don't have quite the resolution that we need for this kind of analysis. And I think Crystal got accepted last cycle as well. That does have the resolution that we want, but it only become public next year. So we keep trying, putting proposals and getting more galaxies.
Good luck for that.
Thank you.